So I'm going to go ahead and rather than starting from add, well, first we're going to do our size method, public int size, return size, and I suppose we should do a constructor as well. So let's move this over here. The class should be at the bottom. Okay, size, public, let's see. Oh yeah, binary search tree, root is equal to null. And let's be explicit because we're going to use root as a variable a lot. So we want to be explicit when we're talking about the root of the entire tree versus the root of a subtree. This dot size is equal to 0. And I find that's where a lot of students get confused based on my previous experiences. In a lot of methods, we're going to be using the root variable. But root, in a lot of times, will be a local variable, the root of the subtree, as opposed to the root of the entire tree. We'll be using this dot root to refer to the root of the entire tree. So, for example, let's go ahead and write that first method, which will be contains public boolean contains item. So we're going to ask, does this tree have the item in it or not? I'm just going to put return false over here just because I don't like having errors. I'll just have to remember to remove that at the end. So remember, these are recursive methods. Or rather, we're going to be writing a lot of recursive methods. So we're going to need actually to use this as a wrapper. Return contains this dot root item. So here we're going to ask, does the root of this tree contain the item? So let's take a look at this. Because again, searching that entire tree is a bit of a pain, so we're going to just do it recursively. Private boolean contains node root item. So here, notice that the root in this case is the root of a subtree, the current root that I'm on. And what I'm saying is, what I'm asking here is, does the root of this tree contain this item? So the first thing we have to do is look at our base case, right? We want to make this simple. So return false, facile, false. So our base case is fairly simple. We're asking if this root contains the item. If the root is equal to null, which is almost always our base case, we're going to say, or the first base case we put in, we're going to say false, no. Okay, and the reason we do this is just simply to avoid a null pointer exception. We do that first so that when we check the item, if the node doesn't actually exist, we aren't going to crash the program. But it makes sense. If the tree is empty, if the subtree is empty, if the current node I'm at doesn't actually exist, makes sense to stop. Otherwise, I'm going to use the compare to method, right? When I do compare to, if I say a.compare to b, we'll get a negative number if a comes before b, a 0 if they're the same, or a bigger number if a is bigger than b. So what I'm going to do is, let's see what I'm going to do. I'm going to do, well, we can do it as a separate variable, but we'll just do it in an if statement. If root dot item, so if item dot compare to root dot item. Just thinking about the order I want to do it. So if this produces a negative number, this means that negative number. So if item dot compare to the item in the root. Well, first off, the first thing I want to check actually is if they are equal. If item dot equals root dot item. Yeah, we're going to do this as a separate value. Int comparison is equal to root item dot compare to root dot item. If comparison equals 0, then those two numbers are then those two items are the same. So return true. We found the item, right? Else if comparison is less than 0, that means that the item I'm looking at is less than the item that's actually in the root. So this comes before this item, which means it's going to be on the left side where all the less stuff is. So we're going to recursively search. Return contains, we're going to search root.left. We're going to go to the left side. We're going to search the left subtree for this item. That's because we know that it's less than the item in the root. So we need to search all the items in the left subtree for this. Well, not all of them, but we've got to search the left subtree for that item because that's where all the lesser items are. Lesser as in, comes before, not as in like implying that some words are lesser than others. Return. And otherwise, if it's not equal to and it's not bigger than, sorry, if it's not equal to and it's not on the left side, then we need to search the right side where all the bigger items or the items that come after would go. And so now that takes it. So most of the algorithms we're going to write are of this method. And they're going to look like this.